This video is going to talk about basic probability vocabulary and notation and a few quick examples. And it's the start to our mini probability section of our statistics unit. So to begin, let's learn the notation for the probability of an event. So this says the probability of event A occurring. So we can use A to represent something. We could actually put words in there, but just recognize that it looks kind of like function notation, but it's specifically asking the probability of something, of the event happening. Now, the probability of something happening must be between 0 and 1, including those values. Because if an event can never occur, its probability is 0, and if an event is guaranteed to occur, its probability is 1. And since the only thing that can happen is somewhere in between there, that's the limit to the probability. The complement, or the probability of not A happening, or A prime, is 1 minus the probability of it actually happening. So you'll hear this referred to as the complement of something. The event itself can consist of many different types of things happening, and we can represent that using the set notation. The sample space, we can call that S. That's going to include all the possible outcomes. Two more symbols we have to learn. You may or may not have seen these before. This says A and B, or the intersection of A and B, and it's when both A and B occur simultaneously. A union B, or A or B, that is when A or B occurs. So like the slide says, these are the basics. These are the things that you're going to have to know going forward. Another important idea that you need to understand, even for basic probability, is the idea that events can be either disjointed or joint. So I think a Venn diagram actually helps you understand that a lot better. So here we have a picture of disjoint events. So A and B. So let's do an example here. Let's say A, the event is that you're a sophomore. B, the event is that you're a senior. You can't be both of those things simultaneously. There's nobody that can fit both of those events simultaneously. Therefore, their circles are completely separate from each other. There's no overlap there. Now, that's important because if A and B are disjointed events, and we're asked the question, what is the probability of A or B happening? It's pretty simple. We find the probability of A, we find the probability of B, and then we add them up. If they are joint events where there is an intersection, that's a different problem, okay? So let's do something where they could be not disjoint. So let's say A is that you have brown hair, B is that you have blue eyes. Somebody can have both brown hair and blue eyes. We're going to use a new word here. This has nothing to do with joint or disjoint, but if A and B are both independent of each other, and we're going to come back to what that means, it's important to know that the way to find the probability of their intersection is to multiply the probability of those separate events. If they are not independent, that is not going to work. And now notice, we didn't talk about how to find the probability of A or B if they are not disjoint. That is something else we will come back to in the future. All right, so here's an example. We started off with a Venn diagram. It looks like one event is basketball, another event is football. These are jointed events, so there's an intersection of those two. And there happens to be something that doesn't fall into either of those, right? That's what that 8 is. Now, when we find a probability, a basic probability of an event happening, we're going to find out how many things would be included in the event that we want to happen, and that will be over the total of things that were the sample space that could have happened. So let's just find a total quickly. So the total of all these things would be, let's see, 64 and 63 and 8, that's going to be 135. There's 135, like these are people. Now basketball, you might just say quickly, oh, 52 out of the 135. That would be incorrect because this 12 is included in both the basketball and both football, right? So it's actually 64 things that are considered basketball out of the 135 total. And same thing for football. It's not just 63, it's the 63 and the 12, which makes a total of 75. And that'll be over the same 135. Right, so that's a very basic probability question. Next, and notice we're not using the letters here to represent the events. We're actually using some language, and that language is going to become very, very important as these get more complicated. Right now, it's pretty basic though. So the next one is probability of only football. So if this is, maybe this is about people and they're identifying what sport they like to watch or the sport they like to play. We want to make sure that we're picking the people that only chose football, not football and basketball. So this would be an appropriate time to use the 63 over 135. And for probability of only basketball, this would be the 52 out of 135. Okay, the probability of neither sport, that's going to be the space that's outside of those circles. So that would be the 8 over 135. And now the probability of basketball and football, that is just the intersection, that would be the 12 out of 135. Right, so like I said, this is the most basic type of probability questions that you can be asked. Okay, so something that we need to be aware of is something called the hidden or problem. It's a problem where, and it's called the hidden or problem because it's really asking you the probability of something or something else happening, but it's actually not using the word or. It's very implied. So here we go. There's a group of 2 women and 7 men. Each person writes their name on a piece of paper, they put it in a hat, and then you randomly choose 2 names from the hat. Okay, the question is, what's the probability that you choose 2 women? All right, so let's think about what we need to know about this. First, we need the total sample set, which would be 9, right? There's 9 people. There are 9 names in that hat. The probability that we choose 2 women. Okay, so that would mean that we would have to choose a woman, which there are 2 of, right? We'd have to choose one of those people out of 9 names. So the chance of that happening would be 2 out of 9. Now, I'm not saying I chose both of them. I'm saying the chance of choosing a woman, right, when they have all 9 names in that hat is 2 out of 9. So we have to now think that we chose that woman when we choose the second time. We chose one of those women, leaving 1 behind. And we also chose a name, therefore there are only 8 names. All right, now, and we're going to multiply those events. So we get 2 over 72. Now that wasn't the hidden or problem yet, and you'll see why. The next question, this is going to be a little bit stranger. What's the probability that you will choose 1 man and 1 woman? Well, what's the difference here? Well, does it matter if I choose a man and then a woman, or a woman and a man? Well, I think that's the hidden or problem. I think we need to find both of those things. So that's what we're going to do. Let's say we took a look at our sample space. Right? A sample space is all of the events that could happen. So we could have chosen a woman and a woman, like the first question asked. But we could also choose a woman and then a man. We could choose a man and then a woman, or we could choose a man and then another man. Right, so we have to consider the probability that we choose a woman and a man, or a man and a woman. And this is that hidden or. We have to now figure out both of these things and add them together. So let's do that. What's the probability that we find a woman first? Okay, so there are 9 names. There are 2 women. Great, we picked out a woman. How many men are in there? Well, 7, because we didn't pick any yet, but there are only 8 names. So that's the probability of finding a woman and a man. Now let's do the other part. Probability of finding a man first, that would be 7 out of 9. But then we take out a name, and there are 2 women there to pick from. And that would be our second part. So if we finish that up, what do we get? 14 plus 14, we get 28 over 72. So see, if you didn't think about the order mattering, you probably would have only answered 14 out of 72. Hence why it's the hidden or problem. We have to remember that. Okay, so we're going to move on to something called the general addition rule. But before we actually talk about what the rule is, let's do an example leading up to it. So I have some US currency here on the screen. And let's say we're looking at a sample space of all of the bills that are in circulation right now. So we have the $1, $2, $5, $10, $20, $50, and $100 bills. And we want to find some special things. So let's say that event A would be bills that have odd values. Okay, so I'm just going to summarize what those would be. So A is really the 1, the 5, and nothing else. And let's say event B is picking a bill that has a building on the reverse side. So I know it's kind of hard to see, but let me help you out with that. That would be the $5. That's the Lincoln Memorial. The $10 looks like, I want to say that's the Supreme Court. I could be wrong. 20, I think that's the White House. And 50 looks like the Capitol building. And then the 100, I'm actually not sure what building that is. I'd be interested though to find out. So there are 5 different things that could happen that we'd want to happen if we wanted B, or event B to happen. Okay, so let's figure out what the probability of A or B happening is. But I want us to use a Venn diagram, and I think you'll see why when we set it up. All right, so we have our whole sample space that has to show up within this Venn diagram. Okay, so we have A, and A would be the 1 and the 5, and B. So now you're thinking, okay, how am I supposed to draw B? You should be asking yourself, am I going to overlap these circles, or am I not going to overlap them? Well, is there any overlap in these events? Yes, there is, a little bit. So let's make our circles overlap. And we know that 5 has to be in that intersection. So if this is A over here, we know that 1 is not in the intersection. And in B, we have 10, 20, 50, and 100 not in that intersection. All right, and did we leave any bills out? Yeah, we left the $2 bill out. That's over here, right, in the neither A or B. Okay, so let's take a look at this. What's the probability of A or B happening? Well, how many things can we choose from? 1, 2, 3, 4, 5, 6. There are 7 things to choose from. And we said that we want to pick from circle A or B, doesn't matter which one. How many things are within these circles? 1, 2, 3, 4, 5, 6. All right, so the probability of that happening is 6 over 7. So why did we do this one with a Venn diagram? Well, remember how we said back here, if the A and B are disjoint events, the probability of A or B is the probability of A plus the probability of B. That was if the circles don't intersect. I told you we'd come back to it. These are intersecting, right? So if I had done them separately, right, the probability of A and the probability of B, and then add them together, I would not have gotten 6 over 7. This right here, this would have been 7 over 7, not 6 over 7 like this one is. And why is that? That's because we would be double counting. So when A and B are jointed events, let's write that down. When A and B are joint events, P of A plus P of B, I'm going to say double counts the intersection of A and B. So we don't want that to happen, right? And that is exactly why we have the general addition rule. So if the events are not disjoint, then the P of A or B problem is still the P of A plus P of B, but we have to subtract what that intersection would be. Because if we counted it twice, we got to subtract one of those out so that it's not double anymore, right? So that's a very important rule to use. Now, other thing to notice is that you could always just use this rule even when they are disjointed, because the intersection would be 0. So you'd just be subtracting a 0 out, right? So that wouldn't really matter. So that's the end of basic probability, because what we're going to go to from here is going to get a little bit more complicated. And that's why our next video is going to be called conditional probability. So see you then.